Now let's return to the idea of the projection again. If we got V here and W here, we have the projection, the vector projection of V onto W, this vector here. That would actually be the vector that lies along here. What I want now is a vector that matches this one. How, in terms of the vectors that we have, can we determine what this vector is? Okay? How would we calculate this vector? So we want a symbolic representation of this vector here. And I didn't emphasize it, but of course that is a right angle. Okay, well, I draw the same triangle over here without W, but we understand it's a triangle whose base is along the line of W. And it's a right triangle, and we have the vector V, we have the projection vector, and I didn't do projection sub W of V, but we understand that I'm just being lazy, and that's the projection that I'm talking about, okay? That would be here. So my question is, can we write down how we would calculate this vector? Now I've written it down here, of course, so it's already given away, but in class we worked on this for a little bit, and I said, okay, well, in class, what two vectors here add up to what other vector? Okay, well, people had a little problem with that because maybe people don't have a good enough picture of what it means to add two vectors, although most people in the class have had statics, and I kind of wonder about that. But you can very easily get lost in the details and the shortcuts of a subject and forget what the basic thing means. It's very easy to do, and you want to try to avoid that, but you know, humanly impossible to always avoid it, but you want to be aware of that tendency. You should, from prerequisite courses, even if you haven't had statics, understand that to add two vectors graphically, you put them head to tail, okay? So what two vectors go head to tail to give you what other vector? Well, it's the projection vector, head to tail with this vector, gives you the vector V, which means, of course, that, well, I've got it over here, that the projection vector plus this question mark vector here has to add up to the V vector. Okay? And I guess maybe I didn't put a head on that projection vector, but nobody would have been able to see it anyhow, so it didn't make a difference. Okay. So, if that's the case, then what is the question mark vector, the vector that we're trying to find? Now I've got a question mark there without an arrow over it, but let's go ahead and put an arrow to be consistent. Obviously, if we subtract the projection from both sides, we get this. So that this vector is obtained by subtracting this vector from this vector. And of course, I didn't draw it in class, but of course that's another good reason to watch the videos. If I've got V here, and the negative of the projection here, then the resultant is the question mark we're trying to find, this vector here. So I'll kind of make that orange, and I'll make that orange, and put an orange circle around this, and hopefully that helps to make things clear. Okay, now, having done that, how can we find the area of this triangle? Okay, well, we're going to talk about areas of triangles and so forth, but the area is the base times the height, base times altitude. Where's the base, where's the altitude of this triangle? Well, if you take the projection vector to be the base, then this is the altitude, and we take half of the magnitude of this, multiplied by the magnitude of this, and we have the area. So that's half of the magnitude of the projection vector, that's half the base, multiplied by the magnitude of this vector, which is the altitude. There's the area of our triangle. And we can talk about the area of the parallelogram that were defined by V and W. We just, make a vector or dotted line parallel to and of equal length to W this way, and similarly with V this way, and we get a parallelogram. that parallelogram contains two identical copies of this triangle, if you wish, but the area of the parallelogram is the base times the altitude. The area of each of these triangles is half of that. The altitude is, again, just V minus the projection of V onto W. That hasn't changed, but now we're doing the whole triangle, so the base is now W, and actually we're doing the whole parallelogram, so the base is W, and the area of a parallelogram is altitude times base, okay, which is just magnitude of this vector times the magnitude of W, so the area of the parallelogram is this, okay. Now there's another way to get the area of the parallelogram, and it's a lot easier, and it involves the cross product, so we'll talk about those implications in the next video.